welcome back. This is Federico. Today I'll be continuing the geometric deep learning series with the Weisweiler-Lemon test. This is one of the key concepts in the graph neural network literature and is still to this day a very kind of active area of research, this area of like expressivity of graph neural networks. So we will start by covering the 1WL test, and you can maybe in your own time have a look at how this generalizes to KWL. So this is really like a hierarchy of tests, and with 1WL being the most kind of basic case. And the problem that 1WL is trying to solve is to say whether two graphs, G and G2, are isomorphic, right? So we want to be able to say, are these two graphs actually different, or are they the same graph? In general, this is being able to say, well, to answer this question in polynomial time is an open problem. So if you manage to solve this problem, you probably become very famous. Anyway, so this 1WL test works as follows. We start with our base graph, and we kind of set each node to some color. And then what we do is we iteratively kind of update these colors. And for example, in this case, we will say that if a node has two blue neighbors, it will be green. And if it has three blue neighbors, it will be yellow. These colors are picked really like, you can pick any color you want. For example, here you can see that this node here, it had two blue neighbors, so we colored it green. And instead, this node here, we colored yellow because it had three blue neighbors, right? And so also this node here, it had two blue neighbors, so we color it green, and so on. So we kind of do this hashing procedure, this color refinement, and we keep going. So we do it again, and now, for instance, we say that purple nodes are nodes which have two yellow neighbors. Red nodes are nodes that have two green neighbors and one yellow neighbor. So for example, this red node here, it's red because we see that it had two green neighbors and a yellow one, right? And so is this one, kind of by symmetry. This also had two green neighbors and a yellow one. This kind of light blue teal, I guess it's called. Instead, we assigned it because it had a yellow and green neighbor, right? So this kind of color refinement procedure is, the colors themselves are very arbitrary, but all we're saying is like we keep kind of going through these iteratively recoloring this graph based on the neighborhood of each node. And then actually, if you run this algorithm again, you'll see that this is kind of like the stopping point, right? So if you do this again, it will give you the same output. And for this reason, you stop, right? And then what you can do is kind of collect a histogram of these colorings. So in this one, you'd say that there's like two teal. Like at the end, you can pretty much say that, well, there's like two teal, there's two red, and then one purple, right? And what you would then do is say, okay, give me another graph. With the same number of nodes, so that kind of these frequencies stay the same. But because if you had more nodes or less, it would be kind of trivial to say whether the graphs are isomorphic. You give me another graph, and then you look at this distribution of colors. And now, if it's different, I can say with certainty that these two graphs are indeed not isomorphic. But if the two kind of frequency of colors are the same, it could be isomorphic, it could not be isomorphic, right? And actually what has been shown, and this was kind of a very big this was a very, very big fact, the fact that some types of graph neural networks are actually as expressive as this 1WL test. And probably the model that introduced this concept first was this graph isomorphism network, so it's called GIN. The authors proved that this GIN model is actually exactly as expressive as this 1WL test, and it can't do any better. And this is nice because now we can finally classify graph neural networks based on their expressivity, and now actually we have neural networks that I believe are up to 3WL and so on. We can craft neural networks that are arbitrarily powerful, right? But obviously being more powerful has some trade-offs, the main trade-off being that of a computational complexity. If you go to these higher order higher order KWL test, then you really suffer massively in terms of computational costs. Okay, well, now that we know that gin, for example, is bounded by 1WL, well, what's the issue here? Well, let's say that I give you these two graphs, so this graph on the left and this graph to the right. Now, these graphs, I mean, just by kind of visually looking at them, they're clearly not isomorphic. This graph, for example, has two 5 cycles, and this graph has two 6 cycles, right? So it seems like a very obvious, I mean, just by visually looking at them, they look very different, and so we should be able to tell them apart. But actually, this 1WL test will tell you that these two graphs are isomorphic, right? So this is a pretty kind of a famous fail case example of this 1WL test. And the issue is, like, actually, if you run these algorithms, what you'll see is that, like, locally these graphs look the same, right? Like here, for example, this node here has 3 neighbors, but so does this one, and this one, and this one, right? So I mean, you can kind of branch out, like you can see that, and you can kind of see this tree structure, and if you kind of overlap this tree structure, both like these nodes will have the exact same tree structure, right? And this is a problem, because these kind of cycles, they're very prevalent in a lot of different tasks. For example, in molecular tasks, being able to distinguish these cycles is extremely important. And actually, it's not that hard to kind of show that this 1WL test is completely insensitive to any kind of connected component of size 3 and above, right? And you can see this like from the fact that, like, these messages are being passed only at a neighbor level. And I mean, this replicates message passing, but then you don't have this kind of global structure that you can extract. Okay, so are we doomed? Well, maybe yes, maybe no. This question is a bit tricky, but there are things that we can kind of do to go around this, and the main idea is feature augmentation. So let's say you have a feature vector xu, right? Now this is, like, I mean, in a regular graphical classification task, each node will have a feature vector, and what you can then do is say that you augment it with some augmentation u. And this augmentation is, again, like a kind of, you can imagine this as another feature vector that you attach to each node, and this can kind of help you distinguish between graphs. So imagine, for example, if you appended information about the cycles in the graph, right? So imagine that now this AU would be a vector, like, let's define it like this. So this would be like how many 2 cycles, let's call them 2 Cs, 3 C, or maybe we should start with 3. 2 cycles is maybe not really a thing. So like 3 cycles, 4 cycles, 5 cycles, and so on. Maybe you end at like 10 cycles, right? I mean, I'm just saying cycles, but you can kind of get stuff that's more easy to compute. Now, let me just fix this a little bit. Now, what you'll see clearly is that, like, in this case, this vector will tell you that there's like the 5 cycles, there's 2 of them, and instead here, this 5 cycle, there'll be 0, right? But then there will be 2 6 cycles, right? And here there will be 0 6 cycles. So already, like this, you can probably see how a graph neural network will be able to distinguish these graphs, even though if at a message passing level it won't be able to. At a feature level, it's able to kind of gather this information to do this kind of stuff. Now, cycles in general are quite expensive to compute, but I kind of invite you to think about, like, the quantity, which is the trace of the adjacency matrix to the kth power. So this quantity is actually related in some way to cycles. You can kind of think about what this quantity means, and yeah, so there are efficient augmentations which you can do, which are, you know, relatively simple, and which should be able to at least a little bit help you to distinguish these graphs. Okay, so this was actually the end of the video. Is more kind of a lighter video, but hopefully still very interesting, and yeah, hope to see you in the next one. Bye.